Hi, today we're going to be talking about nonlinear programming, or NLP, and degrees of freedom in optimization. So previously we've talked about optimization. In Module 7, all of the optimization problems we were solving had a specific format of the objective function, and specifically the objective function we were dealing with was quadratic, which technically is nonlinear. We also talked about some constraints, and we specifically had linear constraints. So just more generally speaking, there's a method in optimization, or a class of optimization problems called nonlinear programs. So a nonlinear program is basically an optimization problem where you can have an objective function that is totally nonlinear. It could be any functional form you wanted, really, and then constraints in terms of equality constraints and inequality constraints that are also nonlinear. So we're going to get into how do you solve these more general, this more general case of optimization problems. We're going to look at a specific optimization problem. So here we have a nonlinear objective function with our two decision variables, and I'm keeping this to two decision variables just because this makes it very easy to visualize the solution space. Those decision variables they're here in this x vector of decision variables, and we're just going to call them x0 and x1. This is going to be an unconstrained optimization problem, except we're going to stick within these bounds of our decision variables. So x0 has to be between -5 and 1, and x1 has to be between -3 and 3. So if we just plotted this out, mapped out this optimization problem, our objective function looks like this, where we have this contour plot, and going down in this direction represents a decreasing value of our objective function. So just by inspection, you can look at this and think, okay, the optimal point is just right here, and that is correct. Some things I wanted to talk about are the degrees of freedom in this problem. So we do have two degrees of freedom. We have our two decision variables, so x0 and x1. And that means when we are looking for the optimal operation of this system, we can have x1 be anywhere along here, x0 be anywhere along here, and then have x1 be anywhere along here. So those are our two degrees of freedom. And we won't actually solve this one, we'll solve the next one. So if we wanted to make this problem, or if we needed to make this problem more constrained, we might add in an equality constraint, which we have not yet dealt with. So again, we have the same nonlinear objective function, the same decision variables with the same upper and lower bounds here, but now we add in this equality constraint function. This would be the g of x equals 0. So if we added in this constraint to our problem, this takes away one of our degrees of freedom, and I'll just show you here. So now we have the objective function plotted, but now I have that line plotted, that equality constraint is plotted on here. So now, because we are solving this problem subject to these bounds being honored and also this equality constraint being honored, this equality constraint takes away a degree of freedom. So now our solutions, this is an equality constraint, so our solutions have to be along this line. So we can say that the numbers of the number of degrees of freedom is equal to the number of decision variables minus the number of equality constraints. And we can also consider the number of active inequality constraints. So in this particular problem, we can no longer vary x0 anywhere along this axis. Rather, all of our solutions have to be found along this equality constraint line. So we can vary our solution anywhere along this line and search for an optimum. So if we had two inequality constraints, let's say we had another equality constraint that looked like that, now we have 0 degrees of freedom. We have no ability to really optimize our system, and we just have to search for the one feasible point, which would be here. But if we take away that second equality constraint, now we're just trying to find an optimum along this line and that optimum would show up right about here. So just a really quick lesson. We're actually going to show you how to program and solve an optimization problem in our next video lecture.